This presentation is delivered by the Stanford Center for Professional Development.
We'll continue. So last time we started looking at this idea, if you can go down the pad here, of the null space of a matrix. Now that's the null space is it's a subset. It's a set of vectors. It's a subspace, in fact, as its name implies, and it is a subset of what I would call, of dimension of the input dimension. That's what it is. So it's the vectors that are mapped to 0. Now what it gives is, this gives exactly the ambiguity in solving y equals ax. So it tells you exactly sort of what you know and don't know when I give you y, about x, when I give you y and y equals ax. In particular, anything in the null space is going to map to 0. So for example, in a sensor or estimation problem, x corresponds to some pattern or input for which your sensors all read 0. So for all you know, it's either 0 or it's something in the null space. If the only point in the null space is 0, then that means that's the only way that can happen. So this is what it means. Now in a design problem or a control problem, something in the null space is a very interesting thing. It's something like this. It's something that has, you might say, 0 net effect. So in the case of the mass problem, it would be a sequence of forces where non-zero. So the mass goes flying off to the left, right, goes all over the place. But the point is that n seconds later, it is back at the origin with 0 velocity. So that means basically nothing happened. Okay? So that's the idea. Now, one case of great interest is when the null space, I can't see if, now it's not me, but that's twisted at an angle. So maybe you guys can rotate your camera there a little bit. Oh well. There we go. Oh, too much. There we go. Actually, that was still too much, but all right. I'll let you guys figure it out back there. So you say that you have 0 null space. That's the slang. That's means simply not that the null space is 0. The null space can't be 0. The null space, the data type is it's a set of vectors. So when you say it's 0, you mean it's a set whose only element is the 0 vector. Okay? But the slang is the null space is 0. And this is, some people call this one-to-one. And what it means is this. It says it is the same as saying x can always be uniquely determined from y equals ax. So it basically says, when does the transformation A not lose information? One-to-one, of course, means that different x's get mapped to different y's. That's what it means. That's actually literally what one-to-one means. Otherwise, you might call it many-to-one, would be the other one. And in fact, one-to-many is not a function, because the definition of a function is that only one thing comes out. So another way to say this is that the columns of A are independent. So when you say something like 0 null space or something, you're really just saying the columns of A are independent. So there's just two different language for exactly the same thing. And you can check that. Why does it mean that? Because when you say AX equals 0 implies X equals 0, AX equal AX, one interpretation of AX is it's a linear combination of the columns of A, where the x's give you the recipe, the coefficients. And so basically it says that the only way to add up a linear combination of the columns and get 0, the only way, is if the recipe is trivial, if all the x's are 0. That's the same as saying the columns are independent. So, okay. Now this part, everything up here is easy to check, or it's basically just a restatement of, I mean, there's nothing to it. This is not obvious, and so a few things here are not going to be obvious. I'm not going to show them now. I'll state them as unproven facts. Later, we'll come back and you'll be able to show all these things. This is an unproven fact. It says if A has 0 null space, if and only if it has a left inverse. Now, left inverse is a matrix B, which when multiplied on the left by A, or sorry, when it multiplies A on the left, it gives you the identity. That's what BA is. Now, you may or may not have seen this. You probably have seen the idea of a matrix inverse, but maybe not a left in. Actually, how many people have even heard of the concept of a left inverse for a non-square matrix? That's good, because it used to be basically no one. So a left inverse means you multiply on the left and you get I. By the way, the meaning of the left inverse is actually, it's great. It's actually a decoder is what it is. Because if BA equals I, Y equals AX, then if you multiply by B, what you get is you get X. So B, when you see a left inverse, it means it is a decoder. Or in communications, it is a perfect equalizer. In any kind of signal processing, it's a perfect deconvolver or something like that. That's what a left inverse is. Okay. Now, what's interesting about this is that sort of course, is a very strong statement about this first one. It says, yeah, you can uniquely determine X given Y equals AX. This says, actually, not only can you determine it, but you can get it by applying a linear function. That's not obvious, right? It could have been that you could uniquely get X, but you had to jump through all sorts of hoops and do all sorts of signal processing or something like that to get X. It turns out, no. In fact, you can decode with a linear decoder. And the next one is this. This actually, it turns out this one is relatively easy to show. It says it's the determinant of A transpose A is non-zero. Okay. At the moment, that means nothing to you, but it will soon. So, and I think this is one of the ones that's this one. I have to be very careful here because some of these are extremely simple. They're either 3 lines or they're actually very difficult. And all the difficult ones, by the way, are equivalent to each other. So, shall I try showing this? What do you think? All right. So I reserve the right to absolutely give up 1 minute into this and to pretend like I never thought that I knew ahead of time this was actually one of the tough ones. Okay? So we're just gonna see. We'll see if this is one of the easy ones. So what we want to show is this. So let's start by saying, suppose that A has a we're going to show that AX, well here, A is 1-to-1 if and only if det A transpose A is non-zero. Okay, let's try that. All right, so let's try a few things here. Let's start by saying, let's assume A were not 1-to-1. Okay, that means, well, by definition, it says that its null space is not just 0. That means that there is some x which is non-zero, but AX equals 0. That's what it means. It means it's a non-zero element in the null space. Okay. Now, if AX is 0, then surely A transpose AX is 0. Because I could write it this way. That's the 0 vector, and A transpose times any 0 vector is 0. But I could also write it this way and write A transpose AX. I can reassociate. But now we have a problem. We have a square matrix here multiplying a non-zero vector, and we get 0. And that implies that the determinant of A transpose A is 0. Okay? So we just showed that if this fails to hold, this fails to hold. And now we do the opposite. Now let's assume that's one way. Let's assume now det A transpose A is 0. Assume that's 0. That means the matrix A transpose A is singular. That means there's some non-zero vector which gets mapped to 0, like that. Okay, where x is non-zero. Now, let me ask you a question here. If I had scalars and I wrote down, actually, can I just cancel the A transpose off of here? That's an excellent question. Can I just write this as A transpose A equals 0 as A transpose times AX equals 0? And now say A is non-zero, so I can just, A transpose non-zero and just remove that. Can I do that? Can you cancel matrices? No. In general, no. You absolutely cannot. Okay? So it's entirely possible. You can have the product of 2 matrices, both non-zero, and you get 0. So you cannot cancel. You can't cancel matrices. Okay? So that's not going to help. But watch this. This is actually, Here, I'll show you a trick. You may have to pan up here. Ooh. It's going to set the pace for the class. But I could move it up. But all right. So what happens is this. We know this. And here's the trick. If this is true, I can certainly multiply on the left by A transpose and get that. Because X transpose times a vector that's 0 is surely 0. So that's the case. Now, I'm going to rewrite this in a different way. I'm going to write this as AX transpose times that. Okay? And that's just one of the rules for transposition. You transpose a product by transposing each thing and reversing the order. Okay? Now you may know that well, I guess it's part of the prerequisite. I think actually for some reason we're going to cover it in a few slides anyway. But in fact, the transpose of a vector times itself is actually the square of its norm. That's actually this. This is actually nothing more than the sum of the squares of the entries. This is AXI squared sum on I. Now, when a sum of squares of numbers is 0, every single number is 0, period. And in fact, what this says is therefore AX is 0. That's just what we wanted, because now I have an X in the null space of A, and it's non-zero, and therefore it's not 1-to-1. So, okay. So I just, by the way, I won't do this very often. I would actually encourage you to see how much of, I mean, most of the statements in the notes are things you should check. These things get boring after a while, but you should actually try to check as much as you can. Most of it is quite straightforward. Some of this stuff for now is not. Okay, so let me say something about the interpretations of the null space. Well, suppose y equals ax it describes a measurement setup or something like that. Then what it says is that something in the null space is undetectable. It's a pattern that is undetectable from the sensors. Because when you have that pattern, all the sensors just give you flat 0 reading. And you don't know if maybe what you're looking at is 0. In fact, it gives you the exact same signature, 0. It also says this. It says that x and x, if you take any vector and you add anything in the null space, they are completely indistinguishable according to your measurements. Totally indistinguishable. So because they give you the same readings, the same y, the same ax. Now, in fact, it characterizes the ambiguity in the measurement. That's what it does. Now, if y equals ax represents something like an output resulting from an input or action x, then basically it says something in the null space is actually an action. It's a non-zero action that has no net result. That's what it means. So, and in fact, in this case, the null space characterizes the freedom of input choice for a given result. So, actually having a big null space in a measurement problem is generally speaking bad, because it means there's lots of ambiguity, if what you're trying to do is recover x. If, on the other hand, x represents an action that you can take and y is an outcome, having a big null space is great, because it says there are lots of x's, and you have an organized way, in fact, of finding x's that will satisfy the requirements. So that's good. And it means you can drop back and you can optimize something else. You can drop back and find a small x or whatever you like that. Okay. Now the range of a matrix is another one of these fundamental subspaces or whatever. So, and it's denoted with a calligraphic R or a script R or something like that. It's range of A. This is also a subspace. It is not a it is a subspace of the output dimension. So it is actually a subset of Rn, and it is simply the set of all vectors you can hit. It's the set of all vectors that have the form Ax, where x ranges over all of Rn. So this is a subset of Rm. Okay? So these are, unless your matrix is square, the null space and range are sets of vectors of completely different dimensions. Okay? Now you can interpret it this way. It's the set of vectors that can be hit by the linear mapping y equals Ax. I mean, that's what it means. It's the set of all things you can achieve or something like that. But it's also, in terms of the columns of A, it's very simple. It's the span of the columns. So So null space 0 means that the columns are independent. If the range here, the range is simply the span of the columns. Okay? And you can also think of it this way. It's the set of right-hand sides, if you write it as ax equals y, for which ax equals y has a solution. So that's the idea. Now, here, it has all sorts of interesting interpretations and applications in different areas. So, for example, if y equals ax represents a design problem, where x is an action, y is an outcome, range of A is the set of all things you can actually achieve. So if someone says, I would like this outcome, but that outcome is not in the range, it means, sorry, I can't do it. I can't get that outcome. Maybe I can get close. We'll talk about that, but I can't get that outcome. In the case of a sensor reading, it's also very interesting. Y equals ax, the range means it is a possible sensor measurement. What would be a practical use for the range in a case like that? Got it. That's it precisely. So what would happen is this. If in fact if you believe the system is modeled by y equals ax, y is a vector of measurements. If a y comes in, and the first thing you do with y is check, is it in the range? If the answer is yes, no problem. You can then proceed to whatever you do. If the answer is no, you want to throw an exception. You want to throw an exception to whoever passed you the y, and basically says, sorry, that y could not possibly have been something of the form ax. By the way, that might mean one of your sensors is off. So this could be a sensor detection routine or something like that. By the way, you could do all sorts of interesting stuff there. How would you check? Suppose you knew that one sensor was bad. What do you do? What's the algorithm? How do you check it? That could be a homework problem, by the way. Want to make a note of that? That's simple. Okay, but let's talk about it. How do you do that? I give you y equals ax. X is in R10. Y is in R20. Roughly speaking, you got about a 2-to-1 redundancy of sensors over parameters you're estimating. But there's a trick. One of the sensors has failed. How would you find it? So I want you to tell me how to find out which sensor. I want you to come back and say it's sensor 13 is no good. How do you do it?
Put in two inputs that should produce the same output and see which sensor it'll match for.
Say that again? You put in two?
You should put in two inputs.
You know what? Actually, it's passive. You don't have, you can't do that. Right, so you don't have the, it's passive. So you can't control X. You're just given readings. That's all. You had a suggestion.
Yeah, take the inner product of y with the rows of the sensor matrix and look at the projection of each sensor.
Okay.
And you'll see something that's 0 probably.
Oh, I don't think you can take the inner product of y with the rows of the sensor matrix, because they have different dimensions. The rows of the sensor matrix are of size Rn, the input, and the output is of size, which is 10 in our example. The others are 20, but you're close. What would you do? Find the null space of what? Let me ask you this. Suppose I have a sensor suite, and I say, please take out sensor 13. What does that do to the matrix? I mean, what happens to, how do you express that in terms of what you do with y equals ax? Y used to be 20 high, now it's 19. How do you get that y, and what do you do with a? What do you do? You delete the 13th row of a. Okay, so that's what you do. So basically, if everything's fine, if it's y equals ax, that's what it's been for a while, and I come along and say, sensor 13 is going out for maintenance. Okay, then you have a reduced a red, and you remove the 13th row. That's what it means. Everybody got this? So now you have a 19 by 10 matrix. Okay, now you can calculate the range of that 19 by 10 matrix. Let's say you can do that. You will within one lecture. You can calculate the range of that matrix. And you can check if the reduced measurement is in the range. If it's in the range, what does it mean after I remove the 13th row? And you have to be careful. What does it mean? It's kind of complicated. What does it mean? I'm going to turn it around and say it means that the 13th, it means if now when you remove a row and you look at the reduced y and it's in the range of the reduced matrix, what it means is this. The 13th censor might not have been bad. Sorry, it's a strange statement, but that's exactly what it means. What if I remove the 13th row, I look at the range of that matrix, I look at the range of that matrix or something like that, and actually now the reduced y is not in the range. It means you still have a bad sense. It means you're still wrong. It means the 13th was not the problem. I'm assuming there's only one censor failure. I have a feeling that I'm just making things more confused. This is what we call a homework problem. You will be seeing this shortly. Trust me. Okay, so, or you can go back and see if any of this makes sense later. Okay, so, all right. Now, when there's a special case, which is when you can hit all vectors in the output space. That's when the range is Rm. That means you can hit everything. That says you can solve ax equals y for any y. That has all sorts of obvious interpretations. We'll get to that. Another way is to say that the columns of A span Rm. That's what it means. Now in this case, this is not obvious. It says there is a right inverse of A. So this says for any y you give me, I can find an x for which ax equals y. This third bullet here is much more specific. It actually says not only that, but in fact I can construct the x as a linear function of y. That's what it means. So here, if in fact there's an AB with AB equals I, that's a right inverse. What it says is this. It says that ABX is x. Well, of course, because IX is x. On the other hand, it just says, you know what? I shouldn't have used x. Sorry. There we go. I mean, it was perfectly okay at this horrible notation. There we go. So what this says is, this is quite specific. It says, oh, you want an x for which ax equals y? No problem. Let's take your y and multiply by b. So b actually is an automated design procedure. That's what it is. If this is a design problem, it's a design procedure. It says, you want this velocity and position multiplied by b. That gives you a force program that does it. Okay, so that's what it is. This is the same as saying that the rows of A are independent. Again, you can check. And it's basically, this is, now it gets tricky. This is the null space of A transpose is 0. Now, some of these look complicated. Some actually are. Most are not. But I'm going to defer a lecture until we show all of the details. So this is the null space of A transpose is empty. And you can say this many ways. These two are actually basically the same thing. Because to say that the null space of a matrix is equal to just 0 is basically saying the columns are independent. But the columns of A transpose are the rows of A. And so this one and this one are simply, that's the English equivalent of that statement. Okay? And this would probably follow from the one on the previous page or something like that. So I want to warn you, some of these are not obvious. But by the way, you should sit down and see how many of these you can actually show. You won't be able to show some of them, like that one. Maybe that one, I'm not sure right away. But within a lecture, you will be able to. Okay. So let's look at various interpretations of range. Suppose a vector v is in the range of a matrix, and a vector w is not in the range. We'll see what does this mean. If y equals ax represents a measurement, then if you observe v, that means it's a possible, or maybe a better name is a consistent sensor signal. We just talked about that a few minutes ago when I confused all of you. Most of you, anyway. If, however, you get a sensor measurement which is not in the range, that basically says it's impossible if you really believe y equals ax, or it means it's inconsistent. That's what it means. Now, if y equals ax represents, and the result of an output given an action, or an input or something like that, then it says, if you're in the range, it's something that's possible. It's achievable. That's another way to say it. However, something not in the range is something that simply cannot be achieved. That's what it means. So in this case, R of A characterizes possible results or achievable outputs, is what it does. OK. So now, so far, we've talked about the size of A has been arbitrary. Doesn't have to be squared. And in fact, what you find my greatest complaint with sort of I mean, aside from the fact that they are profoundly boring, linear algebra classes, the first linear algebra class. My major complaint is that they focus on square matrices too much, which actually in engineering has essentially no use. We'll see why. But in fact, most times in engineering, when you have in any kind of engineering application, you have a square matrix, except we'll see some examples later. But in general, it means something is deeply wrong. We'll see why. You'll know why later, why in fact matrices should either be fat or skinny or something like that. It means kind of you've set things up so there's just enough knobs to turn to do what you need to do. That's silly. The whole point is you want to either exploit redundancy or something like that. I mean, there are cases when you want to do that. If you want to measure something, you want to measure 6 things, and sensors are super duper expensive, and for some reason you can only afford 6, OK, fine. But in general, this makes absolutely no sense. It's not robust either. I mean, in fact, if you have 7 sensors to measure 6 things, at least then you can actually add a nice layer of software that will actually detect and remove a sensor that fails automatically. So using the method that I deeply confused all of you, which you will see on the homework shortly. So, hey, what do you think? Do you think we're allowed to, even though we've posted homework 2, homework 2? I think we can do it. We'll see. We'll see. So, all right. OK. We just have to make it. It may have to wait to homework 3. We'll see. OK. So now we're going to look at a square matrix. You say it's invertible or non-singular if its determinant is non-zero. And this is equivalent to many, many things. See, the things like the columns of A are a basis for Rn. That means they span Rn. That means its range is everything. And it means that they're independent, which means that, in this case, means, well, that's the other half being a basis. So we'll leave that. It means the null space is 0. That's the slang. The null space is the set consisting of the 0 vector. I don't think I quit. I'm going to start saying null space is 0. Okay. It also says the rows of A are a basis for Rn. It says y equals Ax has a unique solution for every y in Rn. So it means it has now, there's a matrix which is both its left and its right inverse, and it's the only one. So if you're a left inverse of a square matrix, you're also a right inverse. Okay? And it's the same as saying the null space of A is just 0 and the range is everything. And it's the same as saying the determinant of A transpose A and det A transpose is non-zero. Now, by the way, for a square matrix, this is easy to show because here I can write this. Det A transpose A is det A transpose times det A. Right? That I can do. Can I do that like here? If I wrote here, that's det A times det A transpose, what would you say to me? What would you say? You'd say syntax error. Exactly. Why? Because det takes as argument only, it takes as argument only a square matrix. And in this problem, there's M and there's N, and they need not be the same. So this is a syntax error, which is a terrible, terrible thing, right? Because it means the most casual parsing would reveal the error. We'll see there later there's some deeper semantic errors. That's where the syntax works out, but the meaning is wrong. Strangely, a semantic error is actually less of a crime. So, OK. But in this case, they're square, so we can write these out, and these are very straightforward. OK. So what's the interpretation of an inverse? Well, I mean, this is kind of obvious. It basically undoes the mapping associated with A. And actually, the cool part is it's both. It can work as equally well as a post-equalizer or a pre-equalizer or pre-filter. And I'm using some of the language of communications here. So in other words, you can, in this case, you can send something through a channel and then apply B to reconstruct what happened. That's a traditional equalizer. Or before you send the signal, you can process it through B. And that has lots of names. Like one is it's like a pulse shaper or I don't know, pre-equalizer or something like that in communications. So that's the idea. Okay. So that's that you've seen. I'll mention one other thing involving that. One interpretation of inverse. Well, in fact, you can also use it for things like left inverses and right. But let's take B as A inverse and let's look at the rows of the inverse of a matrix. Well, let's write this. This is y equals ax, if you write it out column by column, is y equals x1 a1 plus xn an. Of course, x equals by. This first one is y equals ax, and this is just x equals by, because that's the inverse here. Now, if I write this way, I want to write out y column by column, this one, and I'm going to write x out row by row. This says that xi is bi tilde transpose y, because when you multiply a matrix B by a vector y, if you do a row interpretation, it says you take the inner product of each row of B with y. So, did I get that right? I did. Okay? So, hey, that says, look, these xi's, I could plug them in here, and I can rewrite it this way. And now you see the most beautiful thing. You see what the rows of the inverse of a matrix are. They are things that extract the coefficients of, so this basically says something like y is a linear combination of the a's. Now, if you want to know what linear combination, or how do you get the mixture, what's the recipe? It says you take the inner product with the rows of the inverse matrix, and these give you exactly the coefficients in the expansion of A, the expansion of y in the basis A1 through AN. Okay? So sometimes people call A1 through AN and B1 through BN tilde dual bases. And that's actually kind of common now in some areas in signal processing. They call this, and this goes back a long way. And it's interesting actually to work, because we're going to look at some other stuff later, but let me ask you something. What can you say about this? What is that equal to? What is it? Yep, that's 1 if I equals j, and it's 0 if I is not equal to j. Okay? So, by the way, sometimes we're later, actually very soon, we're going to talk about things like orthogonality and things like that. So some people refer to these as bi-orthogonal sets or something like that. In other words, it's kind of weird. It says that the B's are orthogonal to the other A's. But it doesn't, what do you know about this? What can you say about AI transpose AJ? Not much. I can say, there's only one thing I can say. I can say something intelligent about that. What can I say intelligent about that? It's what? It's non-zero. Yeah. Well, how do you know it's non-zero? Right. So I'd have a column of A at 0. What's wrong with that? What would that? I could remove it. So remove it. Thank you. Right. No, I mean, it's all the same thing. I just want, yeah, you can't have, A could not be invertible if it had a column that was 0. Right? Okay. All right. So, well, all of these things are very abstract now, but we'll see them in applications and it will come up. Yeah?
Why you can't say anything smart about AI transpose AJ? Aren't they orthogonal too?
Nope. Mm-mm. Nope, they're not. No, what? But a basis doesn't mean that they're orthogonal. We'll get to that. Yeah. So we'll get to that. By the way, if your background is physics or something like applied physics or something like that, a lot of the matrices you've encountered will be not only square but symmetric, and so a lot of the operators will be self-adjoint, and that means a lot of things you've just because that's what you've always seen. So if that's the case, how's my diagnosis? Okay, that's a diagnosis there. Okay, so in that case, this class is great for you. So you're going to see all sorts of stuff. You're going to learn all the things that are almost always true, like eigenvalues are real for you, right? Yeah, got it. Okay, good. We'll get to that. You'll be fine. Everything will be great. Actually, then it comes up. You'll see it's going to come up in physics too. So we'll see. There'll be cool cases where it's not symmetric. And then weird things will happen. And all your fellow physicists will be deeply and profoundly confused. Because for them, everything is symmetric, all bases are orthogonal, and so on. Okay. Rank of a matrix. The rank of a matrix is simply the dimension of its range. And here are some facts. These are not obvious. Things like the rank of A is the rank of A transpose. Another way to say it is rank of A is the maximum number of independent columns or rows of A you can have. And that means immediately the rank of a matrix cannot be any more than the minimum of its input or output dimension, number of rows or columns. I actually said those backwards, but that's fine. That's what it means, right? So if you have a 3 by 5 matrix, its rank could not possibly be more than 3. It is at most 3. Here's a very, very basic fact. Some people actually make a big deal about this, and they circle it, and it's in some fancy box and everything, and it's called sometimes the fundamental theorem of linear algebra or something. They make a big deal. They have like a theme song. And anyway, so this is sometimes called the fundamental theorem of linear algebra. I mean, it's beautiful, okay, but it's not that big a deal. Actually, you'll find out it's actually much cooler to be able to actually do stuff with linear algebra than to celebrate pretty formulas. It's it's like e to the whatever I pi plus 1 equals 0. It's like, okay, you get over that and then everything's fine. Okay, what this says is actually very interesting. It says that the rank of a matrix, that's the dimension of the set of things you can hit. That's this. Plus the dimension of the null space, that's the dimension of sort of the ambiguity set, the size of the set of things that get crunched to 0 is equal to n, which is the input dimension. And so my interpretation of this, well, I'm sure lots of people interpret it this way, is this is something like conservation of dimension, or if you like, something like degrees of freedom. I mean, maybe that's a better way to say it. So don't take any of this too seriously, but it's just to give you the idea. So the rank of a matrix is actually, it's the dimension of the set hit by, let's make this very specific. Let's take A is in our, well, we just had something that was 20 by 10. That's it. So, oh, by the way, the name for that is technically, that's a skinny matrix because it's got 20 rows and 10 columns. So, and I'll use that terminology. It's going to come up a lot. Okay. So I have a skinny matrix, R 20 by 10, and I'm going to tell you that the rank of A is, by the way, could it be 11? No, but I'm going to make it 8. Okay? So there it is. It's a 20 by 10 matrix. Its rank is 8. Now, what does this mean? It means that if you ask what's the dimension of the what can you hit? What's the set of things that have the form AX? Well, the answer to that is this. It's first of all, that's a subspace of R20. So you have 20 long vectors, and there's a subspace. It could have a dimension up to 10, but in fact, it only has a dimension of 8. That's what it says. Got a dimension of 8. So basically, it says if X is an action and Y is a result, it says that the set of things I can effect or do is actually 8-dimensional. That's what I can do. I can do 8 dimensions worth of stuff. But wait a minute. In this case, I have 10 input knobs. So roughly speaking, you'd look at that and say, well, if what you can do is only 8-dimensional, you have 10 input knobs, you have 2 redundant knobs. Guess what? That's the dimension of the null space. So the dimension of the null space of A, in this case, must be 2 because they have to add up to 10. Okay? And that's the idea here. So it basically says something about like the total number of degrees of freedom you have going in minus the, let's see if I can do it, the degree of ambiguity or something like that is equal to the total dimension of what you can effect. That's kind of what it says. But that's, it's a good idea to have a to have a rough idea of what this is. And then it'll get much more specific in specific cases. So this one is very loose. Like each dimension of input is either crushed to 0 or ends up in output. That's, boy, I would not put that in anything but notes. Because it's actually, in some sense, this is just, I didn't even know what the dimension of an input is. So what I'm saying is, if any of you said this, boy, we'd come down hard on you. I mean, unless it was casual, right? Unless it was in casual conversation. But in anything other than that, you would not want. On the other hand, as a vague idea, it kind of explains what's going on. Okay. Now, there's another interpretation of rank, which is actually very, very nice. It's the idea of coding. And it comes up in ideas like transmission, and actually comes up in compression, all sorts of things. So here it is. If you have a product of matrices, then the rank is less than the minimum of the ranks of the matrices, of the things that you multiply. Okay? Now, this sort of makes sense because if you look over here and you think about, what you can do, it basically says, well, I mean, this one is actually very, very easy to show, this one up here. But now, what this says is if I write a matrix A in factored form, if I write it as if I write B as an m by r matrix multiplied by an r by n, so you can think of r as the intermediary dimension or the intermediate dimension. It basically says I have something that looks like this. That's A. But I'm going to write it this way. I'm going to factor it, and that means basically I'm going to write it as a product of two things. Actually, if you like, instead of one piece of code, it's going to call two, one after the other. Okay? Now, what this says is, in this case, R is the intermediary dimension. It's the intermediate dimension here, is what it is. Now, if you factor something like this, the rank is less than R. But in fact, if the rank is R, you can factor it this way. Okay, so I can write it this way. Now, this doesn't look like it has any. It's interesting. It's actually extremely interesting, and tons of like super practical stuff is based on just this idea. But we'll just look at one now. Actually, later in the class, we're going to do something even cooler, which is this. Very soon, you'll know how to factor a matrix into one to make a factorization like this. And it has lots of applications immediately. Like suppose I want to transmit y given x. But I pay for the number of real numbers I have to transfer between them, right? If n is 100, m is 200, but r is 3, this makes a lot of sense. Because what happens is I do this processing on the transmit side. I transmit 3 numbers, or whatever I said the rank was. And then they're reconstructed over here. So this is already, these ideas should have ideas of efficient transmission, compression, all that kind of stuff is close to here. Is very close to this. So let's just look at one application. Let's suppose I need to calculate a matrix vector product y equals ax. Now you would think, that can't be that big a deal. Why would that be a big deal? And it would not be a big deal if A were, for example, 5,000 by 5,000, right? Or, I mean, it depends on what we're talking here. A could be 20,000 by 20,000, and you could do this, using MPI on a whole bunch of processes or something like that. Or A could be 100 by 100, and you could do this in actually 40 by 40, and you could do this in a shockingly fast way. Okay? I'm just multiplying y equals ax. This could be, what are you doing when you multiply by A? This could be an equalizer. It could be precoder. It could be some estimation you're doing. It could be anything. So we're not worried about that. Now suppose you knew that A could be factored. And let's suppose the interesting case is when the rank is much smaller than either m or n. But let's look at this. Now, if I compute y equals ax directly, that's mn operations, because I calculate the inner product of each row of A with y. And each of those requires, n multiplies and n minus 1 adds. Roughly. Okay? So you do that. That would be mn operations. Okay? With a typical, sort of gigaflop machine. Well, my laptop comes out faster than that. So it's pretty fast. That's okay, because as fast as you can do this, there'll be some application where you want to do it faster, or you want to handle bigger things. So, okay, that would be mn operations. Now suppose you do it this way. You write A as BC, and you associate it this way. You first operate by C, and then by this. Well, if you multiply by C first, it's going to cost you Rn operations, and then it costs you Mr, and that's m plus n times r. Okay? Now, just to plug in some numbers here, let's suppose, well, let's make both m and n equal to 1,000. And let's take r equals 10. So it's a 1,000 by 1,000 matrix, and it's rank 10. The savings now is pretty obvious. In the first case, it's 10 to the 6 operations. And in the second one, it's 10 times 2,000. So it's a million versus 20K. Okay, so that's a 50 to 1 savings in multiplying AX. Everybody got this? So this is the idea. So they're already, I mean, by the way, later in the class, we're going to look at very good methods for not just factors. Very soon you'll know how to factor a matrix this way. If it is low rank, you'll factor it. Later in the class, we're going to do something very cool, where actually we'll look at how to do approximate factorizations. That's even cooler. You'll be given a matrix A. You will know how to find, for example, an approximation of A that's rank 10. Okay? This has tons of uses all over the place. Okay. So that's what it means. If you see a matrix that's low rank, it says actually you could operate on it quickly, or it means it's got something to do with compression or something like that. How do you know if a matrix is low rank in the first place? You will know the sort of exact answer. If you want exact rank, you'll know in one lecture. If you want to know, much more interesting question, much more practical is this. Given a matrix, how do you know if it's approximately rank 10, say? You'll know that in about 5 weeks. By the way, did you notice that I didn't answer your question at all? Okay, just. But I did it forcefully. So that's, okay. So we push your question on a stack. It'll be popped. Okay. So one last topic is sort of change, or another topic is change of coordinates. Now the standard basis vectors are these EIs like this. And you obviously have this expansion. I mean, that's kind of silly, but it's a pedantic way of writing this out. And so this, you would say in this case that the xi are the coordinates of x in the standard basis. I mean, normally you don't say, you just say xi are the coordinates, okay? Or the entries or the coordinates or something like that. So that's how you write it. Now, if you have another basis in Rn, if t1 through tn is another basis, you can expand a vector x in another basis. And we'll call the coordinates x tilde 1 up to x tilde n. Okay? And of course, the fact that that's a basis tells us that tells us two things. It says that the t's are independent, which means there's only one way to write it this way. And it means also that any x on the left-hand side here can be written in this form. Okay? Now, it turns out we can get these x tildes very easily by a couple of matrix operations. So here, x tilde are the coordinates of these. Now, what we're going to do is we're going to write this out as a matrix. So we'll write that as x equals t x tilde. Now, this basically is a 4 ASCII character representation of this. Okay? So you write it this way. But now, immediately we get the answer. T is invertible. And therefore, x tilde is simply t inverse x. And indeed, it turns out that the inner product of the ith row of the inverse of a matrix extracts the ti coordinates. Okay? So, for example, if someone says, I mean, actually, let's see, where would this come up all the time? It comes up in things like vision and robotics. And actually comes up in navigation as well. So for the rest of us, we mostly just use a fixed coordinate system and seem to go through life just fine. But for some reason in things like dynamics and navigation and things like that, everybody has to have their own personal coordinate system. And so you have to transform things from one to the other. Like, for example, in robotics, every link of the robot arm has its own personal coordinate system. And you have to transform them this way. I don't know why people do this, but they do. This is kind of the thing that would allow you to do that. Is this. And now you know what it is. It's sort of the inverse of a matrix, and it's the rows extract the coordinates and things like that. So, okay. Now, you can also look at what happens to a matrix. If you have y equals ax, this is all in the standard coordinate system. And now suppose you write, we're going to write x in the t coordinates, right? And then we're going to write y also in the t coordinates. And the t coordinates will be denoted x tilde and y tilde. Then just by working it out, you get y tilde equals t inverse at times x tilde. That's what it looks like. So this thing is something that's going to come up a bunch of times. Not a bunch of times, but it will come up several times. And you should, it should light up a light in your brain. Well, first of all, it's got a name. It's called similarity transformation. That's the first. And for the moment, this is all very abstract, but you should think of it as basically representing y equals ax, but you represent both x and y in a different basis. And you'll get something that looks like that. So we'll get to that. We'll get back to that later. OK. Now, for some reason at the end of this lecture, there's some stuff that's, I guess, more elementary than all of this and should have been at the beginning, but that's OK. We'll do it now. And it has to do just a quick review of norms and inner products and things like that. Now, the Euclidean norm of a vector is actually the square root of the sum of the squares. So it's written, I mean, in sum of the squares you can write as x transpose x. That's the inner product of a matrix with of a vector with itself. And it's the square root of the sum of the squares. And it's supposed to measure the length of a vector. And indeed, it measures the length of a vector with n equals 1. It's the absolute value. When n equals 2, it's actually the Euclidean distance in the plane. And for 3, it's Euclidean distance in R3. But it makes sense to talk about the norm in R500. Makes perfect sense, and people talk about it all the time. Now, by the way, there's various things related to this. But I'll mention some of the basic ideas. So it's supposed to measure length. It's supposed to be a generalization of absolute value. By the way, some people have actually, the double bars is sort of to distinguish it from the absolute value. So, but presumably if you were super, super cool and kind of just grew up as from a child onward using vectors and matrices, you would probably write this way. And there are people who have reached that level of development, of linear algebraic development, that they write it this way, right? I mean, the same way we've got to the level where 0, we don't mark it. We don't put some doodad on it. We don't put like an arrow on it, like your friends in physics. We don't make it bold or something like that. So for 0, we're fully developed. 0 is totally overloaded for us, right? It's like it's the same thing for the number, the complex number, matrices, vectors, everything. So this is a holdover. Actually, it's 150 years old, or maybe more, something like that. But at least it looks like it. Now, there's only one minor catch here. Unfortunately, there's a bunch of fields where it's useful to interpret this as the element-wise absolute value. So that's the hitch there. So anyway, but it's supposed to be a generalization of this. So it satisfies a bunch of properties. These are all easy to show. This one, I believe you did show or will be showing. Is that right? No, it's close to something you'll show or will be showing, which is the Cauchy-Schwartz inequality. Is that right? On this homework. OK. I'm always a couple of homeworks ahead, so I can't remember. OK. This is a triangle inequality. It's kind of obvious. It says, basically if that's x and that's y. It says that's x plus y. And it says that the length of this is no bigger than the length of x plus the length of y. And then the picture makes it totally obvious when they would be equal. And that's when x and y are aligned. That's it. OK. That's non-negativity, kind of obvious. And this is called definiteness. It says that if the norm is 0, the vector is 0. That's easy to show here, because if the square root of a sum of squares is 0, the sum of the squares is 0. But if a sum of numbers that are non-negative is 0, each number is 0. And that means each xi squared is 0, and therefore each xi is 0. Now, there are some things related to norm. For example, it's extremely common in a lot of applications where n varies. By the way, if n doesn't vary in an application, like if you're doing control or something like that or whatever, people don't, when n is fixed, it's like 6, and it's the 3, positions and the 3 momenta. You don't divide by n or something like that. But in other areas like signal processing, where you get vectors of different lengths. For example, if just an audio clip is a vector, but n depends on what the length of the audio segment is. And you want to talk about different things like that. Or it could be any other signal. It's extremely common to normalize the norm by square root n. That's the same as taking the sum of the squares of the elements, dividing by n. This is called the mean square value of the vector x. And that is obviously the root mean square value. That's the RMS value of a vector. And it just gives you a rough idea of the size of what it's a typical size that the entries would be. There's actually some things you can say about it. But so if the RMS value of a vector is 1 or 1.3, it means that basically if you look at a random entry, it should be on the order of 1.3. By the way, if a vector has RMS value 1.3, how big could the entries be? Could they be 1,000? Could you have an entry that's 1,000? What? Yeah. Dan? Okay. Yeah. So I'll simplify your answer. Ready? Yes. That's his answer. It's correct. You can have a vector whose RMS value is 1.3, and you could have an entry in it that is 1,000. But that only works if you have a really big vector. You'd have a lot of zeros and then a really huge one. So you couldn't have a forlong vector that had an RMS value of 1.3 and have an entry 1,000. Okay, so, and there's things you can say about that, but that's the rough idea. Now, norm gives you is length from 0. If you take, since you have a difference, it says the norm of a difference gives you a distance. This is very important. This allows you to talk about the distance between two things. This is what allows you to do things, talk about the distance between, for example, two audio signals or two images. You can say, and in fact here you might even give an RMS value. In both cases it would be very interesting. What would you do? You might have the original and some encoded and subsequently decoded signal, and you'd say I was within 1%. The RMS error is 1%, meaning that means the norm of the difference divided by the norm of, say, the original signal is about 0.01. That's what that would mean. So that's the idea. Okay. Now the inner product, of course, we've been using it all the time. It's it's lots of ways to write it, but one way is this. It's actually just x transpose y. It's nothing else. And in fact, I don't think we won't write this. Actually, it's kind of cool. There's other ways people write this. I'll show you some of them. Here's one that you see. Again, we're going towards physics now. This would be the notation there. And there's others. You could write x comma y. That's one way. And I've seen this. You can also do a dot. And then depending on what subfield you're in, your dot is either a little subtle thing or big, thick thing. So anyway, so these are different notations for inner product. Actually, does anyone know any others? Because there's probably some others too. But yeah, well. All right. So okay. So the inner product. I mean, you can work out these properties. This is quite straightforward. In fact, I think I won't say much more about that. I'll just zoom on because these are kind of obvious. The Cauchy-Schwartz inequality, very important, and it says this. It says that the inner product of two vectors in absolute value is less than or equal to the norm of the product. And from this you can immediately derive, for example, the triangle inequality right away. But that's what this says. And this is something I guess you show on the homework, or have shown, or will show in the next half day or something like that. The angle between two vectors is simply, it's the arc cosine of the inner product divided by the product of the norms. Now, this number here is between plus and minus 1. And the arc cosine, let's draw the cosine. So we usually take it between 0 and 180 or something like that right. So we don't distinguish between minus 10 degrees and plus 10 degrees. It's the unsigned angle is the way to say it. So it's the angle between things. And this allows you to do all sorts of cool stuff, to talk about two images and say that they have an angle of 3.7 degrees with respect to each other. Makes perfect sense. Or an image can come in and you can have a database of 10,000 images, and you could ask which of the 10,000 images does the one that just came in have the smallest actually the largest inner product with, which would mean the smallest angle. And this would make sense, and you can already start guessing these things have applications. So, but you can talk, I mean, it's kind of weird to talk about the angle between two vectors in, for example, R1 million, because that's what you're doing if you're looking at 1K by 1K images. Okay? So after a while, don't try to visualize, by the way, R1 million. Or at least work your way up there, because you could be, yeah, in big, yeah, just don't just start with like R4. When you're comfortable in R4, go for R5, maybe R8, something like that. And it also may take there might be some drugs you might have, some pharmacological things are needed to really, really understand R. Actually, Tom Cover gives a wonderful talk basically showing beyond it makes it completely clear. You know, we pretend, so people ask like, what the hell are you doing here? We're talking about the angle between two images. There's no such thing as the angle between two photos. And I go, yeah, sure, it's 3 degrees. Then I'd say, oh, no, let me explain. Oh, you don't understand. See, we do this kind of applied math stuff. And the way it works is we talk about distances and angles, but in huge dimensional spaces. And they go, can you really visualize that? And then at that point, you have the choice of either lying and saying, oh, yeah. Or saying, no, then what you'd really say if you weren't, is you'd say something like this. You'd say, well, no, not really. I mean, the truth is not even close, right? But you'd say, well, not really. But you see, we use our pictures that we draw on like 2-dimensional paper, or, you know, in our offices when you get a grad student say, hey, hold your hand up here. And then you get in there and you poke around this way. And you say, well, we use that to guide that. We use that intuition from R3 to guide us in making, you know, let's say image compression algorithms in R1 million, right? So you might ask, well, how useful is your intuition from R3? And Tom Cover has a series of examples showing that you know nothing, that basically anything, he'll show you all sorts of things. They'll be true for like n equals 3, 4, 5. For 6 on, they're just total, they're so false it's amazing. And it's things where like, you're like, wow, that's, anyway, I should collect some of these from him because they're really good. I mean, there are about 4 of them. I mean, one is like, you know, if you're in the unit, if you pick a point at random in a unit ball, in a unit ball in like R20, it's basically, I think they call it sphere hardening. There's something like a 99.99999% chance that you're within 1% of the boundary of it, of the sphere, on the boundary. So just totally insane things. But okay, just to let you know, just so that at least we were honest about it. Okay. So it's very important to understand what it means to have like a positive inner product or a negative inner product or something like that. Oh, I should say this. If x and y are aligned, that means they point in the same direction. That says that the inner product is the product of the norms. If they're opposed, that means that the inner product is as small as it can be. If they're orthogonal, it means that there's a 90-degree angle between them. It means x transpose y is 0. And it's very important to understand what it means to have a positive inner product or a negative inner product. So positive inner product basically means that the angle between them is between 0 and 90. So that's, you know, if you have two things, as you twist them out, the inner product goes from, the angle goes from 90 as you open it up, and the inner product is quite positive. It's as positive as it can be when they're aligned. As they twist along like this, and when they get to 90 degrees, the inner product is 0. And there's 90 degrees, then the inner product starts getting negative, like that. So a very, very crude thing to say would be something like this. If the inner product between two vectors is positive, they point roughly in the same direction. And I mean really roughly. I mean they're not fighting each other. I mean if you add them, they actually help. In fact, that's actually one of the characterizations, that the norm of x plus y is bigger than whatever the norm of x plus norm of y or something like that. It's bigger than the minimum of the two. Anyway, you make progress. If you have a negative inner product, it means they're actually the angles between 90 and 180, let's say. So this allows us to define things like a half space. If you have the set of x's who have a negative inner product with a given vector y, that's this. You draw the vector y, and the vectors that have a 0 inner product with y, basically those that are orthogonal to y, that's the hyperplane with y as a normal vector. That's here. This shaded region, these are actually vectors whose inner product is negative with y. So they have an angle more than 90 degrees. So that's sort of the picture. This is called a half space, and these things they come up and all sorts of things. It's a half space is the solution of a linear inequality. Okay, so I'll start on the material of the next lecture, which you've probably seen in one or two other contexts, maybe in the context of like Fourier series or somewhere. So we'll talk about orthonormal sets of vectors, the Gram-Schmidt procedure, or when you write it out as a matrix, in matrix terminology, it's called the QR factorization. And then we'll talk about various things we can show with this. So, okay, so we start with the idea of an orthonormal set of vectors. So a set of vectors is called normalized if norm ui is 1. So normalized just means the length is 1. Okay? And by the way, some people call those unit vectors. I don't know why. Another people call them direction vectors, vectors whose norm is 1. So that's very common notation for it. Unit vectors is a bit weird because for most people, unit vectors means like, EI, E3, E5, but still. A set of vectors is orthogonal if different vectors in the set have 0. So another way to say it is like mutually orthogonal or something like that. It says that any two vectors in the set, different vectors in the set, have a 90-degree angle between them. Okay? And it's orthonormal if both. Now, watch out, because people will simply say, you will say on the streets, U1 through UK are orthonormal vectors. Okay? That is basically, it's completely wrong. By the way, there's nothing wrong with saying U1 through UK are normalized vectors. That's cool, because to be normalized is an attribute of a vector alone. To be orthogonal, it makes no sense to say, if it made sense, then you could have your set of orthogonal vectors and mine. We could throw them together. If you have 5 and I have 7, now we have 12 orthogonal vectors. Doesn't work that way. Normalized vectors works no problem. We can combine your normalized vectors with mine, and now we have 12 normalized vectors, but they're definitely not. So orthogonality refers to a set of vectors. It is not an attribute of a vector. Okay. Now, how do you write that in vector notation? Very simple. If you have some vectors U1 through UK, you put them in a matrix like this. So you just simply make them the columns of a matrix called that U. And to say this is simply to say U transpose U is I, period. That's it. Why? Well, because U transpose is U1 transpose up to UK transpose like this. And then you multiply by U1 through UK. And you can see now the II entry of this matrix is basically UI transpose UI. That's 1. And the off diagonals are 0. So what would be the matrix way of saying that a set of vectors is orthogonal, but not necessarily normalized? How would you say it? Yeah. U transpose U is diagonal. That means that's a mutually orthogonal set. What's the matrix way of saying a set of vectors is normalized? How do you say that? It's, let's see. In terms of U transpose U, it would be the diagonal entries of U transpose U would be all 1s. How about the off diagonal entries? Who knows? That depends on the angles between them. Okay, so that's what it would say. Okay, now you can quickly show that orthonormal vectors are independent. How? Well, if you write something this way and you multiply by UI, you'll get just that alpha I is 0. And that says that if you have an orthonormal set of vectors, U1 through UK, then it turns out it spans R of U. Okay? Now you have to be very, very careful here, because if I say that if I have an orthonormal set of vectors, that's exactly the same as saying U transpose U is I. Exactly the same. This is the matrix way to say that. Okay? Watch out, because it is not the same as that, although that will hold in some special cases. Okay? So it's general. This is not true. And actually, there's a quick way to remember it. Okay? If you have a bunch of matrices, and a bunch of vectors, and you stack them up, like, let's see. So here's 3 vectors in R10. So I write them this way. And I write this, right? And so you get a 3 by 3 matrix here, right? Like that. That's U transpose U equals I. Okay? Now, suppose I got confused and switched them around, and I wrote U transpose equals I. By the way, there's no syntax crime here, none, because this would be a 10 by 10 matrix. This would be a 10 by 3 matrix, and that would be a 3 by 10 matrix. And there is no syntax crime. So a casual parsing doesn't reveal any problem with this. So the parser goes right through it. Okay? But there's a quick way to know that you're in deep, deep trouble, and that's this. When you multiply 2 matrices together, the rank of this matrix is 3, the rank of that matrix is 3, and the rank of the product, therefore, is at most 3. And what's the rank of the identity matrix in R 10 by 10? It's 10. So we have a problem here. So this is a semantic error if you do this. Okay? It's a semantic. Now, by the way, we're going to find out that 10 by 10 matrix is not the identity. What it is really interesting, and we're going to see later. But for the moment, it's not. Just remember, it is not the identity. Okay. I'll mention the geometric properties, which are actually very interesting. Suppose you have an orthonormal set of vectors, which is to say a matrix whose columns are orthonormal. Ooh, that was slang. Did you hear that? But I'm trusting you that you're cool on that and aren't going to make semantic and other errors. But anyway, that was slang. But that's how, by the way, people would say it. Otherwise, you'd sound like a pedant, right? If you're like, excuse me, don't you mean the set of its columns is orthonormal? So anyway, you shouldn't talk to people like that. You should avoid them. Okay, so suppose the columns of U are orthonormal. All right. Then it says the following. If you take W equals UZ, it says that the norm of W is the norm of Z. Now note that the norm of W it's a different, W is possibly a different size from the size of Z. Different size. So what this says is when you multiply by a matrix whose columns are orthonormal, you don't change the norm. That's what it means. Another way to say it is people say it this way. W equals UZ is isometric. Iso means the same, and metric means that it has to do with the metric or distance properties. And it basically says if you have 2 points like this and the distance is 3 between them, if they get mapped by U, it says that the distance between, if that's like x and y, the distance between ux and uy in possibly a higher dimension will also be 3. So it preserves these things. It's very easy to show this. I mean, that's just a quick calculation. And I think maybe this is a good time to quit for this lecture. Great.